Dear audience, it's my pleasure to introduce this talk on the cleavage stress promoting crack path deflection and anisotropic fracture in cold drawn paralytic steel. Here you have the beautiful logo of the University of Salamanca, 800 years old, the oldest in Spain and one of the oldest in Europe. We are four authors: Jesus Toribio, Beatriz, Gonzalez, Juan-Caros, Matos, and Francisco-Javeier, Ayaso, the Fracture and Structural Integrity Research Group of this old-fashioned University of Salamanca. Summary outline of the presentation into 5 parts: introduction, experimental procedure, experimental results, discussion, and conclusions. First of all, the introduction. Motivation. Scientific interest of this study is the fracture behavior of pre-stressing steel and its relationship with the microstructure, with a special emphasis in crack paths. The importance of the study, the analysis of the relationship between fracture microcracking and the cold drawing process. The aim of the work, a study of the fracture behavior of paralytic steels with very different degree of drawing, with observation of the fracture surface and calculation of the deflection angle of the crack path, determination of the critical loads in the load displacement plot, FU, search of the relationship between critical loads and microfracture processes in the vicinity of the crack tip. Second, experimental procedure. We have used a paralytic steel without a toy composition, 0.8% of carbon and other elements. From the whole roll bar, 0 drawing steps, base material that is not cold drawn at all, green color, left hand side, in red, orange color, the cold drawn wire that has undergone 7 drawing steps. This is commercial pre-stressing steel wire. The microstructure of the steels in the left hand side, green color, the whole roll bar, in the right hand side, orange color, the cold drawn wire. While the whole roll bar exhibits a randomly oriented paralytic microstructure in both transverse and longitudinal direction, the fully drawn material exhibits in the transverse direction a more or less non-oriented isotropic structure with curved cementite, but in the longitudinal direction it exhibits a markedly oriented microstructure, oriented and enlarged in the y-axis or cold drawing direction. The evolution of stress-strain curves, sigma epsilon. Here we represent the plots stress versus strain for increasing level of cold drawing. We can observe a clear improvement of mechanical properties, yield strength and ultimate tensile stress as a consequence of the cold drawing process. The testing procedure, we perform axial fracture test in a universal testing machine shown in the photograph, and we are interested in both macro and micro crack paths. The macro crack paths is observed by optical microscopy and visual observation, and regarding micro crack paths is observed by scanning electron microscopy and fractometallography in addition. Let's go to the third part, experimental results. With regard to the macro crack paths, here we represent the results in both horizontal and profile for slightly drawn steels and for heavily drawn steels. Slightly drawn steels, left hand side of the slide, left column in green color, heavily drawn steels in orange color, right hand side of the slide. While the slightly drawn steels exhibit an isotropic fracture behavior with propagation in mode 1 following the initial fatigue propagation direction, transverse direction, with certain roughness, the heavily drawn steels exhibits an isotropic fracture behavior with local micro deflection and even a macro crack deflection angle with propagation in mixed mode and a strong component of mode 2. Here we observe the microcrack paths in slightly drawn steels with certain branches and bifurcations, and with regard to heavily drawn steels, the microcrack paths exhibit also crack branching, bifurcation, and local deflection. Let's go to the discussion. Here we observe the microcrack paths for heavily drawn steels. We observe a certain propagation in mode 2 and mixed mode, anisotropic fracture behavior, crack deflection, crack deviation, and even axial cracking separated from the initial crack tip. We observe in the load displacement curve an up-in phenomenon in the form of micromechanical bursts and vertical walls consisting of enlarged and oriented cleavage appear in the fractographic analysis in the fracture surface. These vertical walls correspond to the propagation step with a deflection angle near 90 degrees. In addition, brittle fracture mechanism taking place locally in an instantaneous and unstable manner. This is a local instability, but with posterior-ulterior increase of load, the pop-in phenomenon. This pop-in phenomenon is associated with heavily drawn steels with an isotropic fracture consisting of micromechanical bursts is associated with this enlarged and oriented cleavage, vertical walls of fracture shown in this micrograph or fractograph. In addition to this burst, we observe axial microcracks produced by the cold drawing process itself are potential fracture initiation places in vertical wire direction. In addition to this fractographic analysis of the microcrack paths, we have performed a finite element numerical modeling of the stress distribution just to analyze which is the stress responsible for this crack deflection associated with this mixed mode crack path. After this numerical modeling of the loading process of the pre-cracked sample pre-cracked by fatigue, we observe similar CTOD, crack tip opening displacement, to that obtained under cycle loading, fatigue. Material is characterized by means of the stress-strain curve. And large displacement and updated Lagrangian formulation was used. The numerical modeling is shown here. This is the level of loading sigma C, critical axial stress, divided by 100. 100th of the critical load for fracture. We increase the load to 1/10 of the critical remote stress for fracture. We observe the increasing stress. We represent sigma XX, that is the horizontal stress, could be responsible as cleavage stress, responsible of this vertical wall, vertical steps, and crack deflection angle next to near 90 degrees. We increase the load to the half of the critical remote axial stress, and we represent the horizontal, the sigma XX, perpendicular to the remote axial stress, which is oriented in the y-axis, called rowing direction, or ZX axis. For the critical remote axial stress, for the critical applied load, we observe a clear crack tip blunting that shifts the maximum horizontal stress, sigma XX, towards an inner position, farther from the notch tip, thereby provoking vertical cracking by cleavage in heavily drawn steels with strength anisotropy. And this cleavage stress is not just at the notch tip, but at a certain distance, just the place where this vertical cracking probably appears. Here we represent the profile of this cleavage horizontal stress, the X component of the stress tensor, for different levels of loading, represented by fractions of the sigma C critical axial stress, critical externally applied axial stress for 100 part, from 1/10 for the half, and for just the critical load. We observe how the maximum value is shifted towards positions far from the notch tip. Then the conclusions. 1. Cold drawn pre-stressing steel wires exhibit strength anisotropy in the form of fracture path deflection towards a direction approaching the wire axis, or cold drawing direction. Such an anisotropic behavior is a clear macroscopic consequence of the perlitic microstructural orientation induced by the manufacturing procedure at the two levels of the perlitic colonies and lamella. Crack path deflection is initiated at certain nuclei fracture regions at which axial cracking appear in the cold drawing direction or wire axis in the form of micro cleavage units and a pop-in small burst, sudden local fracture. This cracking produces a sudden and small decrease of load in the load displacement curve, the so-called pop-in phenomenon, as a consequence of the slight loss of bearing capacity of the sample. The cleavage stress, sigma xx, is responsible for this locally deflected cracking, axial microcracking, appearing at a certain distance from the crack tip or from the blunted crack tip, in addition to the pre-damage at the micro level after cold drawing. Finally, an epilogue remembering Fray Luis de Leon at the University of Salamanca. Fray Luis de Leon was professor at the University of Salamanca, a major Spanish poet, and he wrote in Spanish, "Qué descansada vida la del que huye el mundanal ruido." In a more or less rough translation to English, we could say, "What a quiet life for those who escape from the noisy world." And with the beautiful logo of the University of Salamanca, 800 years old, the oldest in Spain and one of the oldest in Europe, I say that's all. Thank you very, very much for your kind attention.